Okay, let's get started. So, welcome everybody to another edition of SNAPP. It's my pleasure to introduce today Florian Dörfler. So, Florian is a professor at ETH Zurich, where he's affiliated with several centers, including the AI Center, Energy Science Center, and the Learning Systems Center. He's an expert on automatic control and optimization, and he's the recipient of several prizes, including recently the 2025 Rossler Prize, as well as the Manfred Thoma Medal and the European Control Award. And so today we're delighted to have Florian here to tell us about strategically robust game theory via optimal transport. So please, Florian, take it away.
Sure. Thank you very much for the introduction and the kind invitation. I hope you can all hear me clearly. If not, just interrupt. So it says here, joint work with a guy called Nicolas Lanzetti, who was a PhD student of mine until recently, but it's not just joint work, it was really his work, a culmination of his PhD thesis. Nicolas nowadays with Caltech in the group of Adam Wehrman. Further, there were some math students involved, Andreas Feix and Fricker, and two other senior consultants, Vito Bolignani and Dario Paganian from Imperial College. Okay, what's the main motivation of this work? As control theorists, we are interested in, many of you, decision-making and uncertainty. One of the problems we're sometimes confronted with is autonomous driving. And of course, in autonomous driving, there's plenty of sources of uncertainty. But the main one, the tough one that is hard to model and to combat with is sort of the behavior of the other agents. How should you model them? How should you model their intentions? How can you model any uncertainty you have around their intentions? But what is helpful in this type of paradigm is that the other agents are strategic too. They're not random. They also have a mission, like they want to get from point A to point B. And this sort of paradigm of decision-making under uncertainty, where the main uncertainty is the strategic behavior of the other agents, is not just in autonomous driving. We can also find in other fields, most prominently the stock market. I mean, if you want to make money in the stock market, what is most important is that you model a strategy of your competitors that are also buying stocks. And of course, you have an uncertainty quantification around that. Like, let's say, security allocations. How do you secure the pyramid of an airport? You want to model the possible invader and defend against that person. And there's a few other examples you can make up. So what are the sources of uncertainty? Let's stick to the autonomous driving example here. Of course, there's the exogenous uncertainty, that the infamous lightning strike hitting you. Truly exogenous, hard to model, not much you can do about it. There's also uncertainty that comes with limited information. That is, you only have partial information about the environment, so limited sensing capabilities, and you need to make a decision based on limited information. Yet another one is limited rationality. That is, your assumption is the other agent is strategic, but they might not be entirely rational. So they might play best response. They do what you think is best for them, but not always. So there might be a source of randomness there as well. And last, of course, limited computation, especially important in any sort of real-time control settings that everybody intends to be rational, everybody wants to make the best decision, but it's just hard to compute what is the best decision. Okay, so these are sort of the classical sources of uncertainty you can consider in this problem. How do you deal with them? Well, in an ideal world, you would try to isolate these different uncertainty sources and you would try to model them. So I said, for the exogenous uncertainty, there's not much you can do. The best you can do is, try to get some bounds in it, try to model it, and make a probabilistic decision. Maybe that's the least interesting here. The others are more interesting. So what do you do if you have limited information about the world, about your environment? I guess the dominant paradigm nowadays is the Bayesian paradigm, namely just put a prior on it. That is, you don't know exactly what's going on, but you have a prior belief. And there's an entire field about game theory that is dealing with that, called Bayesian game theory. There might also be the issue of limited rationality. That is, the other agents play best response plus minus some random epsilon. There's an entire field discussing it called behavioral game theory that is related to that. And last, when it comes to limited computation, it's well known that it's hard to compute, for instance, a Nash equilibrium or a Nash strategy. There's the entire field of algorithmic game theory working on that. So each of these uncertainty sources has sort of their own dedicated subcommunity working on it. But in practice, it's very hard to, isolate these uncertainty sources. They always come together, and it's very hard to model them. Plus, there might also be the issue of uncertainty being somewhat endogenous, which is not captured by any of those. And that's what I'd like to dive into today. I'd like to motivate the theme of the talk with a very simple example. It's a game, very simple one. There's a car that wants to drive along the road. So if you follow my cursor, it just wants to go straight. And there's pedestrians that want to cross the road. Okay, and there's different strategies you can play. The car can maintain its speed. It can decelerate or stop. Like with the pedestrian, can wait on the side or cross. For instance, if the car maintains speed, it gets a payoff of 10. The pedestrian has to wait, it gets a payoff of -1. On the other hand, if the car maintains speed and the pedestrian decides to cross, they both lose. There might be fatality. So both get here a -50 and a -100 in payoff. So this is a very classical version of a matrix game. 3 actions for the car, 2 actions for the players. And you might wonder, what are the equilibria, the Nash equilibria for this game? I'll use the word Nash equilibrium right now in a very hand-waving way. I'll later define it, but it's sort of the best response. Everybody does what is best for them, assuming everybody else also does what is best for them. So in this game, there's 2 different Nash equilibria, or 3 to be more precise, but one is not relevant. One is the situation where essentially the car wins. So it maintains its speed and the pedestrians win. The other Nash equilibrium is the car stops and the pedestrians cross. Here, essentially, the pedestrians get their right of way. There's also a third mixed Nash equilibrium that sort of plays a probabilistic strategy, like 50% here, 50% there, but it gets a lower payoff after all, and that's not relevant. So these are sort of the 2 Nash equilibria that you may take as a solution to this game. Now, is this Nash equilibrium robust? Well, think about you in this Nash equilibrium. That is, the car maintains its speed, the pedestrian waits. Well, that doesn't make much sense if you have any sort of uncertainty about the pedestrian possibly willing to cross. That is, this Nash equilibrium is very fragile. You get 10 in the nominal case, but you may lose -50 and the pedestrian may lose -100. So in this case, Nash is maybe not the right strategy if you want to be robust. In this case, robust to the worst case outcome. And there's another notion of solution to a game called the security strategy. That is, you want to play the best response given the worst case outcome. So you play the sort of max-min strategy. So of all the actions the car can take, it takes the one where no matter what the other agent does, it loses the least. So here, the car essentially gets 0 if it stops, no matter if the agent waits across. And it avoids the worst case of -5 and -50. So that's called the security strategy. Let's just focus on the action of the car right now. Let's leave the pedestrian side. So if the pedestrian has any sort of probability of crossing, what you do? You can play Nash, so you maintain your speed, hoping the agents wait, or you can just stop, hoping that the pedestrians also would stop. Of course, in this situation, nobody moves, so it's not a very desirable equilibrium. So let's plot the performance of these 2 equilibria as a function of the probability that either of the pedestrian crosses. Okay. So the vehicle payoff, if you play the security strategy, so you just stop, it's always 0. It's 0 no matter what the percentage is, what the probability is that the pedestrian crosses. Nothing changes. Okay, it's a safe strategy. Nothing bad can happen. What about the Nash equilibrium? Well, if you play the Nash strategy, that is, you maintain your speed. If the agents don't cross, or the pedestrian does cross, you get a payoff of 10. But if there's any tiny probability of the agents crossing, you see that your payoff actually very steeply decreases. The worst case, you have fatality, so you go to -50. I also plot here the variance of that decision. So you see both the variance branches are quickly and the expected values fall. So the conclusion is the following. Nash is nominally a good strategy, but in case of any uncertainty, it's not a robust strategy. Whereas the security strategy is very robust, but you get a very low payoff. Okay, so that's maybe well known. Similar to control, you can play optimal control or robust control, has the same trade-offs. But is there another equilibrium to this game that might be of interest? Well, it's not necessarily equilibrium, but I argue that's what any of us would do. Any of the listeners here, if you drive a car, you see some pedestrian on the sidewalk, and you wonder, will they cross or not cross? I argue probably all of us would decelerate, right? We wouldn't maintain our speed. We wouldn't go on a full stop. We'd just go slower. And if we go slower, well, we lose a bit of payoff compared to maintaining a speed strategy. So we go from 10 to 9. But we also avoid the worst case fatality that's possibly killing pedestrians. Because if we hit them with, say, walking speed, then we only get a payoff of -5. So that seems to be the natural choice any human would make. But this does not necessarily correspond to any game-theoretic equilibrium, which is strange. So what would this natural strategy turn out to be? So nominally, if nothing happens, you get 9 here, right, which is a little bit lower than Nash equilibrium. But as the probability increases that the pedestrians cross, this strategy deteriorates very gracefully. That is, the mean is decreasing only slightly. It quickly outperforms the Nash equilibrium. Say if your probability of crossing is beyond 3%, you outperform the Nash equilibrium, and you have a very low variance with that strategy. So the takeaway is this very natural strategy that a human will adopt. It does not correspond to Nash or security strategies, but it's more robust and performs much better. And what this talk should do is just to formalize that notion of an equilibrium. What is it? Does it make sense? Can you say anything about it? How would you define it? How would you compute it? What are its properties? Okay, this natural strategy. Good. So this is what we call strategically robust equilibrium, and I will now give you a formal definition of that. So we have the standard game-theoretic setup, in this case, n players indexed by I. I runs from 1 to n. Each player has an action space, A1, A2, and so on, and the overall action space is just the product space of all of these. What about the strategy space? Well, every player, say in this matrix game, can choose one of its actions with a certain probability. So the strategy space for player I is just the simplex delta I. Okay, so it can choose any of the strategies with non-negative probability, such as the probability space defined over this action space. What's the expected utility? There's a utility UI that comes with action AI of player I, and with action A minus I for all the other players. So if you're not familiar with game theoretic notation, the index minus I means everybody but I. So it still depends on your own decision, but also on everybody else's decision. As said, for your own decision, you can have a strategy in the simplex. That is, you can choose different of the actions with certain probabilities. So this is probabilistic, and you take here the expected value over this probability distribution, PI, that you pick. But likewise, the other players, of course, can choose what is called mixed strategies. So they can choose a probability over the different strategies. So you also take the expectation over the probability of the other players. And you see it's already getting very interesting at this level, because you somehow need to model how are the other players choosing their probability distributions. And that's a tough one to model. And to do this, we use the notion of ambiguity sets. So now I'm getting a bit closer to my comfort zone, where I more come from. So those of you that know distributional robust optimization, DRO, that you probably heard about ambiguity sets, let me introduce them graphically. So you want to model the probability of the other players choosing the action P minus I. And maybe you have a nominal guess for that one. Say you can just construct it from some past historical decisions, for instance, or you have a prior information on that, but you might be inaccurate. And to make sure you cover this inaccuracy, introduce what is called an ambiguity set. It could be, for instance, a ball, like this B should mean ball of radius epsilon in the probability space around your nominal guess of the other player's actions. Let me keep it at this hand-waving label so far. Of course, now I need to be precise and make sure, what is the ball? What is the metric we consider? Does it only apply to finite variance distributions and the end? But let me keep this deliberately, hand-wavy, and I'll make it more precise later. So we have an ambiguity in terms of we don't know how the other agents make the decisions. We don't know the P minus I, the strategies, and we want to robustify that. Okay, so we have these ambiguity sets, and then we need to make what is called a distributional robust response, best response. So we don't play best response, we play the best response in face of the uncertainty that we don't know the strategy for the players that may take this P minus I may take value in some ambiguity set that I need to model right now. Okay. I'll go into how we model these ambiguity sets in a bit, but just to give a preview, the notion that we eventually settle upon will be some sort of Wasserstein distance. Okay, let's revisit the two classic equilibria that we looked into as strategies. One is the Nash strategy, where I say, the probability that player one chooses over its action space is the following. It just plays best response. That is, wants to choose strategy that maximizes the utility of all possible strategies in the simplex. Okay. And when I maximize this, I also need to take into account the strategy of the other player. Well, the other player does the same. The other player also plays the best response, and we both play argmax, that gives a fixed point. And this fixed point is called the Nash equilibrium. We both play best response, assuming the other guy plays best response. And we saw Nash equilibrium is sort of nominally works well with a previous example, but it may also be fragile. The alternative is the max-min strategy or security strategy, where, let me just slide this here to the side. Okay. Where what I do, I play the best strategy, assuming the other guy does the worst case. So I play my best response and assuming the other guy choose any strategy over its simplex. So I can choose anything here on the right-hand side, and I want to robust to anything. So I play the max-min, the robust response. And likewise, the other player plays the max-min, so all the robust response. So this is sort of the optimistic version of Nash equilibrium, and that's the robust version. And now what we want to do is the following. We want to define the strategically robust equilibrium, where say, I don't think the other plays best response. I don't think the other guy plays also a security strategy, but I think the other guy plays any strategy within an ambiguity set. So I have a nominal center of a ball in the space of strategies, P2 bar, and now take any epsilon. So I take any strategy count and epsilon ball around the other player. And now I play max-min, where I minimize of all strategies the other player can take inside a ball centered around this nominal strategy, P2 bar. And likewise, the other guy does the same. So it's sort of a way to interpolate essentially between Nash and security strategies. In fact, the idea behind this is say, if I reduce the radius of this ball of the ambiguity set, I don't know what the other guy does, to 0, I get back to the Nash equilibrium. That is, you play best response, you play best response. If I choose the radius of this uncertainty ball very large, then I get back to the security strategy. Okay, here I get absolute infinity. And now I interpolate between the two. So I want to robust to the other guy's decision in the space of strategies. And that's our definition of strategic robust equilibrium. Every player I choose the best strategy. So PI bar is in the argmax over the min, where we minimize over any strategy the other players can take in some epsilon ball centered around a nominal strategy P bar minus I. And this happens for all I. Notice what is quite implicit in this definition is when I want to determine P I bar, it depends on the other guy's strategy P minus I bar. And so you again get back to the Nash fixed point argument that everybody assumes what the other guy is playing. So the center of this uncertainty ball is sort of implicit and has to come out of this fixed point argument. So the challenge is, there's many challenges when you write down this definition. One is, how do you even evaluate that? So if I'm a player and I want to solve this game, I want to play the best response, I have to solve a distribution robust optimization problem. Is I need to make sense of this max over my decisions, min over anybody else's strategy in an ambiguity set. And so how do you even solve this? Is this solvable? And the other question is, you can write this down, this very implicit equation that couples Pi bar and P minus I bar for every I, but will this equation eventually have a solution that does exist a fixed point, just like the Nash strategy? So is there an equilibrium? And those are the two questions we set out to solve here. And of course, does this make sense? So now I have to define a little bit more closely what I mean by ambiguity sets. In his work, Nicholas developed a theory for quite general abstract ambiguity sets, but the most useful one will eventually be an optimal transport-induced ambiguity set. Let me introduce that. So you want to describe ambiguity. You want to describe uncertainty in the space of probability distributions. And you want to take a ball that is centered around a nominal distribution, this red one, and you ask, how should you choose this ball? And the desired specifications for choosing such an ambiguity set, a ball in the space of distributions, is it should be expressive. It should protect you against many different sources of uncertainty, against ideally all other distributions. It should be tractable. That is, the problem you write down should be solvable at the end of the day. And last, you want to be able to interpolate with this uncertainty ball. That is, if you shrink the radius of this ball to 0, so if the radius is 0 of this ball, you want to recover the center. Okay. Likewise, if you put the radius of this ball very large, so you take an infinity, you want to cover the entire space to the entire simplex. So it should have these properties. And so we went back to the playbook of distribution robust optimization and checked which notions of ambiguity sets people consider there, what are the pros and cons, and would they apply here as well. And so the classic ones are optimal transport-based ambiguity sets, divergences, or moment-based ambiguity sets. And they're all within our desired specifications come with their pros and cons. Maybe let's look at the moment-based ambiguity set first. So if I specify the uncertainty of a distribution by the moment, so I want to capture all distributions whose moments are sort of epsilon away from the moments of the center distribution. And that is a reasonable specification. In practice, if you dial this down to finitely many moments of distributions, and then you lose this nice interpolation property that is, if I put the epsilon to 0, I don't recover the center of the ball. So if I specify distribution only by 2 moments, then there are many, that's not uniquely define the distribution, right? There's many distributions that could have these 2 moments. So the moment-based ambiguity sets don't have this nice interpolation property that, it shrinks down to the center of the ball as you reduce the uncertainty. KL divergence is another obvious one. As you know, KL divergence makes sense only if the 2 distributions you want to compare have the same support set. If they do not have the same support set, KL divergence essentially is infinity. So it doesn't have a very good resolution. And so we also ruled out that one in terms of it's not extremely expressive. You only can compare distributions of the same support. And what we're left with was the optimal transport-based ambiguity sets. And I guess that's also what the TRO literature settled to, because they essentially cover all of these properties. So they are interpolating, they're expressive. About tractability, there has been a lot of recent progress in the last 5 years, so they become ever more tractable. I guess they're not quite as tractable as the others, as you can see them there, but we're getting there. Okay, so let's narrow our definition down to optimal transport-based ambiguity sets. Just a refresher for everyone, but I guess in this audience you probably all know it. What is optimal transport? What is the optimal ambiguity set? So you have 2 distributions, P and sigma, and you want to have some notion of distance between the 2. The way you write this distance is to ask yourself, what's the amount of work, say, a worker has to put in to shovel that dirt pile to that dirt pile? That is, you have a distance between any point on the left side, xi, any point on the right side, xj, and then you sum over all I over all j and sum up the distance dxi xj. Now you take the expected value, so you take this times a probability gamma ij, where gamma ij is some sort of joint distribution. Okay. For instance, gamma ij could be the product distribution between sigma and p. It could be that, it could be any other. What is important that the gamma ij has the right marginals to say if I sum over one of these columns here, I get back this element of sigma, which is what this equality says here. So the column sum recovers sigma, likewise the row sum should recover p, or in more standard language, the marginals of this joint distribution gamma should be just p and sigma, the 2 distributions you want to compare. Now there are many such distributions you want to compare, and so you minimize all possible gamma, all possible distributions that have the right marginals. And that's, at least in a discrete world, a very simple way to introduce this optimal transport distance, denoted by W, which is distance between P and sigma. W stands for Wasserstein. And so that's how we define our ambiguity set. We say the way we want to capture uncertainty in the other player's decision is the following. It should be any strategy, sigma minus I, that is at most epsilon away from the nominal strategy, P minus I, as measured in this Wasserstein distance, in this optimal transport-based distance. So that's our notion of uncertainty for the other player's behavior. We also have, of course, all the results in the continuous action space. The only difference when you go to continuous action space, you don't have sums anymore. You go over integrals. So here's the integral over the 2 distributions. In a specification, the marginal over the joint distributions has to be sigma and p. And now there's not anymore a min. You have to take an inf. And to be precise, it should be defined only for the distributions gamma for which this integral is finite. So you normally assume a finite variance distribution space. But everything extends under enough assumptions. Okay, so that's our notion of strategic robust equilibrium. And we wonder, we can write this down, but is there such an equilibrium, right? I can write down this particular notion. So every player chooses the best response So argmax, assuming the other players play any strategy within that ambiguity set, the Wasserstein ball centered at the nominal strategy of radius epsilon. Okay, so that's the existing equilibrium. It doesn't come for free. You need to make assumptions, but the assumptions are rather mild. That is, they will essentially boil down to the same assumption you normally make when you want to construct a nominal Nash equilibrium. So the assumptions are either that the action spaces of the players are finite. So you go essentially over finitely many actions, and you can then essentially choose, your probability is just a vectors. Or you assume the action space of every player, AI, is continuous, so it's a subset of Rn. And you assume that subset to be compact, so that the max makes sense. And of course, you need to make sure every payoff function ui is continuous. Otherwise, the maximum doesn't make sense. So these are the assumptions here. And they're rather mild. And if either of these two assumptions is true, then you can show for any value of epsilon, even epsilon is equal to 0 when you reduce to Nash, then such a strategically robust Nash equilibrium exists. Which is great news, because these are the same assumptions you write down for existence for standard Nash equilibrium. Okay, so there's nothing different here. So essentially of course, the proofs behind are more complicated, but the assumptions boil down to the same assumptions as for Nash equilibrium. To give you a few tidbits about what is behind it, as you can see, what is this equation? It's a fixed point equation, right? So pi is a function of something on the right-hand side that depends also on pi and p minus i. And we write this for i. So essentially, it's a bunch of fixed point equations, and you want to apply a fixed point theorem. Like Nash famously applied Kakutani, but you can also go to others. But if you want to apply any sort of fixed point theorem, you make sure that this function on the right-hand side has the desired continuity properties. Also, since you maximize, you want to have some concavity properties. So the hard part of the proof is to show these regularity assumptions. So you want to show that this inner problem, this distribution robust optimization problem, that the solution of that is actually concave in pi, and it's continuous both in pi and in the other player strategies. If you prove these regularity assumptions, you're in shape to essentially set up a standard fixed point argument. And a lot of the math behind this proving these regularity assumptions, which is not that exciting to talk about. That's why we'll glance over that. But conceptually, it's a very similar proof as for the Nash equilibrium, with many more levels and layers of details involved. Let's go back to our example here. So we had these three strategies: security, blue, which is robust; Nash, the bronze, which is nominally great, but very fragile; and this very natural strategy, which means you decelerate simply. It turns out if you analyze that problem and you compute the strategically robust equilibrium as a function of the probability of the pedestrians crossing, so essentially this plays the role of your epsilon, your uncertainty set, that is the other player can modulate between wait or cross, then you can formally show that the Nash equilibrium is actually a strategically robust equilibrium for low values of epsilons until here roughly. And beyond that point, sort of this natural strategy, as I call it, is a strategically robust equilibrium. So you would have then this type of behavior here. So it turns out our natural guess, what we would have done as a driver, really corresponds to this notion of strategically robust equilibrium. So we are successful in this case in formalizing this behavior. Good. Now the question is, how do you compute it? Existence proof are normally easy in math, right? Showing something exists, like you apply, for instance, Brouwer's fixed point theorem, you know there's a fixed point, yeah, good for you, but you have to compute it in practice. So how do you compute the equilibrium here? And there's a long line of work under the name of algorithmic game theory, where people showed these Nash type definitions are normally very innocent. They look nice, but it turns out computing Nash equilibria, even for very benign, innocent matrix games, is not that easy. When you go beyond two players, it's actually quite hard. It falls in a class of complexity called PPAD, which let me try to recall what it is. It's parity, polynomial arguments, parity over directed graphs, something like that. It's a class of complexity problems in computer science. What I normally remember, it's not the hardest class of problems. It falls somewhere between P and NP. that is computing a Nash equilibrium. You cannot necessarily do it in polynomial time unless you have two players. But it's also not an NPR problem. It falls somewhere in between, and it can be reduced to a directed graph search problem. So that's where Nash lands. It turns out computing a security strategy is rather simple. You can do this in polynomial time. And as I told you, the strategic robust equilibrium is somewhat interpolate between Nash and min-max. So the question is, where does this line fall? Is it a straight line between? Is it like going up here? Is it going down? We don't know. So that's what we'd like to understand. How hard is it to compute the strategically robust equilibrium? And the result we can show here is the following. That is, the computational complexity is the same as Nash. So for any epsilon greater 0, the computational complexity of computing a strategically robust equilibrium has the same as the Nash equilibrium. It's in PPAD in that class. We actually conjecture it's lower than that. We actually think it's somewhere down here, but no guarantees yet. Ongoing work by Nicolas and Dario in this case. But at least we know it's no harder than Nash. How do you find this equilibrium in practice? There's different strategies you can apply. One is to go for a complementarity problem. Essentially, you write down the KKT conditions of all these argmax and min problems, and you just treat all these KKT equations as a big set of algebraic equations, and you tackle it this way. So this derives to what is called a complementarity problem, where you want certain variables to be non-negative, like Lagrange multipliers. You want other variables to be either 0, like gradients or gradients being aligned, or non-negative. And you have complementary slackness condition that this x and f of x should be orthogonal. So standard KKT conditions type. And you can throw in solvers that the people have developed in algorithmic game theory. So for certain problems, it's known that you can compute this very efficiently, like for two-player games or polymetrics games. But in general, it's hard, but the people have developed solvers for that in algorithmic game theory. Okay, so let's apply these solvers for a bunch of examples and see what comes out. So numerics. And that's what I think is the most fun part about these equilibria. They give rise to some unexpected behavior. So here's a simple game, 2x2 matrix game, free rider game. So there's two players, perfectly symmetric. They have to achieve a common task. They can either cooperate both in achieving this task, and they both get a payoff of 0.6. They can both choose to not cooperate, and everybody gets 0. They don't get anywhere. However, if one of them cooperates and the other one does not cooperate, then the guy who does not cooperate, he essentially is a free rider. He gets for free the win, so he gets 1, and the other guy is listed to work, so he has 0.6. And it's perfectly symmetric there. So it's a scenario we all know from daily work. There's free riders that benefit from the others. And you wonder, okay, what's here the best strategy? And you can show there's two Nash equilibria, pure Nash equilibria. Essentially two diagonals, that is one cooperates, one does not cooperate. So these are the two Nash equilibria. But of course, these are very fragile again, because any sort of tiny deviation of that strategy would lead to both getting 0. So again, it's nominally a good Nash equilibrium, but it's very fragile. That is, if the other guy does not play best response, you both lose. There's another mixed Nash equilibrium, which is more robust. And then a mixed Nash equilibrium goes as follows. With 60% we cooperate, and with 40% we do not cooperate. And both do this. And it turns out this mixed Nash equilibrium is more robust in the following sense. That is, if you now, again, model a probability of anybody deviating from their strategy. So epsilon is the probability of deviating. So it's also our robustness radius and ambiguity set. You can show that you get a robust benefit of 0.6 is your payoff in that game, no matter the probability of the other person deviating. Okay, so it's a very, in this case, more robust Nash equilibrium. You always are at 0.6. Now, what happens when you play the strategically robust Nash equilibrium or strategic robust equilibrium that we defined before? Something interesting happens. That is, in case everybody sticks to the best response, it's the same as the Nash equilibrium. But as soon as there's a probability of somebody deviating, it's different from the Nash equilibrium. Surprisingly, you get actually a higher payoff than Nash equilibrium, which is surprising when you see it for the first time. So if you don't play best response, but you play best response assuming the other guy does something slightly weird, so you robustify the other guy's strategy, actually both players benefit So it induces some sort of coordination between two players. So surprisingly, in this way, both players are better off. And of course, uncertainty reduces. So you see the uncertainty set is shrinking here, which is very puzzling. We don't have a full mathematical description why this happens, but we see this across many examples. That is, if you do not stick to your selfish best response strategy, but you allow some slack, you're both better off. So that's an interesting observation for this example. Let's go to another example, the inspection game. So there's a worker and an inspector. The inspector can decide to inspect or not inspect. The worker can work or shirk, that is, just slack off. And of course, ideally, the worker would like to slack off and not be inspected. So he gets a 10, and the inspector gets a -10. And of course, the other cases may also occur. So what are the Nash equilibria here? The Nash equilibria is just you play each strategy with 50%. So half the time the worker works, half the time he shirks. Same for the inspector. Inspector does not expect. These Nash equilibria are again robust, so they're not fragile in this case. That is, you get a solid payoff, in this case of 5 for the worker, no matter the probability of the inspector deviating from his strategy, and the same for the inspector, gets a -2.5. And again, we could now compute a strategic robust equilibrium. So we give ourselves an ambiguity set, epsilon, and we assume, for instance, on the worker side, the inspector may, for instance, nominally inspect or not inspect with 50% probability as indicated here, but also account for a probability epsilon of the inspector deviating from his strategy. And again, you get this coordination effect. That is, if you both robustify to each other not playing best response, you're both better off. That is, you both times shrink the uncertainty and you both simultaneously get higher payoff. So it induces some notion of coordination, which is very interesting to observe. We could not fully characterize yet when that happens. It happens for many games, but not for all. So we're still trying to understand when and why this coordination happens. But it's definitely quite counterintuitive if you see it for the first time. That is, by robustifying, you induce coordination. Last example, I heard there's also a queuing theory audience, so you may appreciate that one, the Brest paradox. So quite famous one. So you have cars that want to go from S start to T, which is the terminal goal you want to reach. There's two routes. You can either go the upper one or the low one in case there's no bridge. So in the middle, if that bridge does not exist, the optimal solution is just split the flow half-half. So half goes top, half goes to the bottom. That's both Nash and security strategy. Interestingly, as soon as you have the bridge, there's many more options. So for instance, you could go the expensive way, 9, 0, 9, so you get 18. Or you aim for a cheap way. So if you're the only one going there on this arc, you get here 5, 0, 5, so you get 10. So it seems quite cheap. But of course, both want to aim for the cheap route. And that's why it's called Brest paradox. That is, if you include a free bridge here, it turns out everybody will lose. That is, the social cost, the total travel time when introducing this bridge is higher for everybody. So we can also now compute the Nash equilibria and the strategic robust Nash equilibria for this one. So here will be the Nash equilibrium, so the travel time for both players, if you have two of them. Again, plotted over epsilon, the probability of the other player deviating from the strategy. It turns out on average it's 18, which is this one, and there's a small variance around it. What I plot down here, the dashed line, this would be the travel time if there was no bridge, because if there's no bridge, one player goes here, because cost of 14, and there goes here, also cost 14. So that's the nominal case, you have no bridge. If you compute the strategically robust Nash equilibrium, again, something very surprising happens. You reduce the travel time of both players, and you actually get all the way down to travel time as if there was no bridge. Again, quite puzzling. We haven't fully understood that, but again, it has this flavor of if you robustify to the other person's decision, you induce a level of coordination. The way I explain to this myself not as a scientist, but as a car driver is the following. If we're in traffic and we all insist on our best response, we know that just creates chaos. But if we sort of are willing to take into account and anticipate the other guy's actions plus some slack, so we don't know exactly what they do, but we prepare for whatever the other guys do, then typically traffic flows smoother. So that's how I explain to myself this somewhat paradoxical behavior. But as I said, the math is still to be understood. We haven't fully figured it out yet. Good. A few more minutes. Tiff, when should I stop roughly?
I'd say in the next like 7 to 15 minutes or so.
Okay, perfect. I'm gonna go on for another 8 minutes roughly. So this was all about discrete games. So you have a finite number of actions. You can also do everything in the continuous case. You have a continuous action space, and then you need to go to the continuous Wasserstein distance. So it gets slightly more technical, but it can still be done. So the proof of existence still goes through. But what a computation. Okay, so all the examples I used to motivate things before are continuous games. That is, you don't have a finite number of actions, but you can typically choose among a continuous action set. Likewise, the famous Pepsi versus Coke game that I use later on. So what are the challenges when you have a continuous action set? It turns out the space of strategies, I mean, it's the space of probability distributions over the reals, for instance, and that's infinite dimension. Okay, so it's just a much more complicated object to deal with. And just even evaluating the Wasserstein distance itself is difficult because the Wasserstein distance was defined as the min or the inf over all distributions which have the right marginals, which itself is a tough task. It's, you could phrase it as an LP, but it's an infinite dimensional LP. So here's sort of the main ideas in the continuous case what we can show. We already showed existence of an equilibrium, but we can actually show that there's a pure strategically robust equilibrium, meaning the solutions we're aiming for, there might exist mixed strategies, but it turns out there's always a pure strategy. There's a single action that is as good as any mixed action. So it simplifies your life. So you just need to search for pure Nash equilibrium, just one action. The way we do this under the hood, we use duality theory for the distribution robust optimization. So we apply standard ideas from DRO, how to dualize the Wasserstein distance problem, and then get to the solution. I will, let me just share a few details, not too many, we're already at the end of the time. So that the space of mixed strategies is infinite dimensional, so you need to make some assumptions. So you assume you have work on compact action spaces and convex action spaces. You need to assume your payoff functions are continuous functions, okay? And you need to show that they're concave. These are sort of the assumptions you need to apply the fixed point theorem and to show existence. And under these assumptions, you can show that there is, most importantly, there's a pure strategic robust equilibrium. That is, there's a single action. There's not a distribution of actions, which once you know you only search for a pure action, it makes your life much easier what to look for. You don't need to look for a distribution of actions. Second, about evaluating the Wasserstein distance. It turns out there's quite some tricks in terms of duality, which you can play. You can essentially take the standard results from DO literature, and you can show instead of evaluating the min over all distributions, you can also dualize that problem. And it would look something like this. Details are not so important. I just want to show you in the inner part of this bracket here the following. That is what you evaluate when you compute your optimal decision is your cost, UI, your payoff. But then there's also a cost from the other guy deviating from its nominal strategy. That is, the other guy has a maybe nominal strategy A minus I. He can deviate from the strategy. So there's an A hat minus I the other guy can choose. If you deviate from the strategy, incur a cost. Okay, and that cost will be the Lagrange multiplier of the Wasserstein constraint. And you can also then just solve the problem in this way after dualizing it. And so at the end of the day, you solve essentially, again, a standard Nash equilibrium problem with different cost functions. That's a little bit what is behind the hood. The math is just dualization. Let me conclude this with an example, the infamous Pepsi versus Coke game, the Cournot competition. So we have, in general, N firms, like Pepsi and Coke, those are two, that compete in T markets. In this case, there's one market. Every firm, I, can produce for a market T. Okay, that's the action. Okay, every firm I can produce for market T. What's the profit? Let's look into this term first. So that's your production. Whatever you produce, there's a certain price you pay, which is inside the blue part. I'll get into this in a second. And there's a certain cost you have. The cost is just linear. Okay, so there's a linear cost in producing good I, and it's CI. Okay, and you sum over all markets T. So the sum is not so important when you only have a single market. What is interesting is the price that you get when you produce. The price that you get is an affine function of what everybody else produces. That is, if there's a lot of production, of course, the overall price drops. And what's important is this here is a quadratic function in your own actions, and it's bilinear in terms of there's products of, say, A1 and A2. Okay, so the price in market T depends on what everybody else is producing for that market. So there's a quadratic cost function here, and that's called the Cournot competition. You can also try in constraints, that is, the total production of all markets is in some set. Not so important. And you can, again, for this Cournot competition, which is now continuous, so you can choose your AI anywhere in this continuous set. Let's look into the Nash equilibrium. So the Nash equilibrium, in this case all firms are symmetric, so everybody gets the same parameters, alpha and beta here, and everybody gets the same C. Then the payoffs of all these firms would be, in this case, around 1,000, or sorry, slightly less, 900 here, okay? And there would be some uncertainty, plus minus 300 in that Nash equilibrium, okay? And what I plot here is the performance of Nash equilibrium plotted over the robustness level, that is when the other players have a probability of deviating from the best response. And again, it's a robust Nash equilibrium, nothing bad happens. If you have this strategic robust equilibrium, again, you would induce some sort of coordination. That is, if everybody robustifies to their guys not playing best response, they might deviate from the best response in some ambiguity set of radius epsilon. Then actually every single firm, so that's 1, 2, 3, 4, every single firm would actually increase its payoff and reduce its variance, which is quite nice. So that happens until a certain point when you sort of over-robustify yourself, and then performance drops. But there's surprisingly, this is a concave function, and there's quite a large range of sweet spots where if we all are robustifying to each other, we all win here. This conclusion is fairly robust. That is, you can show this also happens when the markets are not symmetric. So if everybody takes different values of CI here, it turns out these curves will look slightly different, but they still qualitatively resemble this concave curve here. Again, that's an effect we have not fully understood, but I thought I'll share it here just because it's very cute and to be figured out. Good. In conclusion, so I presented here this definition of strategically robust equilibrium. That is some sort of robustification of a Nash equilibrium. That is, you protect your agents against deviations in the other agent's behavior. The way we model this uncertainty in the other agents is we construct an optimal transfer-based ambiguity set in their decision space. Okay, so we assume they play maybe nominally best response, and we robustify to all epsilon nearby actions measured in Wasserstein distance. It turns out, a fact we have not fully understood, is that often you get higher payoff for all agents that induces some sort of coordination effect. And I left this really deliberately as an open problem here. And what is interesting in terms of the math you can show behind the hood is that the definition looks complex, but there's no additional cost on top of the Nash equilibria. That is, the assumptions you need for existence are the same, and the complexity class of computing them is also the same, which is a quite nice independent result. Good. Thank you all for listening, and of course, open for questions.
All right, let's thank Florian for a great talk. And then we have some time for questions. So feel free to just unmute yourself.
Florian, this is Armin. It's a very interesting talk. I have this. How do you enforce consistency in the sense that when I saw my local max-min problem, I get like a solution. What if it's not even in the support of the opponent? Or is that a requirement? Everything has to be in the support?
Let me go back to somewhere where I have the definition up here. Maybe here. Okay. So how do you ensure consistency? So what you need to make sure is that this inner function has all the properties that you need to set up the standard Nash fixed point argument. That is, this inner function is actually a continuous function both in your action and in the other player's action. It turns out that does not come for free. You need to make similar regularity assumptions, among others, the continuity of the cost function, but also you make sure you cannot choose any ambiguity set here. It turns out for Wasserstein ambiguity sets, this comes for free. Otherwise, it may not be the case. That is, you cannot show that this inner problem here will yield a function that is continuous in the other player's actions.
I see. Thanks.
Yep.
Okay, I have a couple of questions.
Sure.
Okay, so I think the simplest one, perhaps obligatory, but did you try prisoner's dilemma style examples where like basically there's sort of coordination to be induced that's not even near the normal Nash equilibrium?
This is somewhat similar to the prisoner's dilemma. In the prisoner's dilemma, you can also have defect, or you both keep silent. So it turns out for the prisoner's dilemma, it's more or less similar to this one with slightly different numerical values, but you get similar conclusions as for this one. Yes.
Okay, cool. I also had some questions about the so you discussed the sort of first about the assumptions for the continuous existence proof, or sorry, the continuous computation proof. So is it that for the existence of the pure equilibrium, you need the additional concavity? You need an additional concavity assumption in this case?
Okay. Here, yes. No, that was the same assumption as before. The proof is now slightly different, so that the previous proof already assured existence, but here we can go beyond and show that it's a pure equilibrium. But those are the same assumptions as before. Yeah, no additional assumptions.
I see. So we needed concave payoffs already.
Yes, we needed concave payoffs already. The reason being the fixed point theorem that we apply needs that the function is concave.
Okay, but what does that mean in the finite support case?
Sorry. Let me go back.
Or was that concavity of the mixed strategies with respect to the mixed strategies? That would make sense, but
yes. Let me go back here. So
okay,
we're left here. So before we needed to show that this entire object is concave. This is concave. Sorry, in the continuous setting, we also need to show that the inner one is concave. Correct. So there's two UIs, a capital and a lower one.
That's what I was missing. Okay, thanks for clarifying. Yeah. Okay. And then I think that clarification actually answers my other question too. So yeah.
Okay. That's good. As I said, the most puzzling effect of everything is this coordination that is induced by being robust, which we haven't understood, but it seems to occur quite often, not always, but very often. So.
Yeah. It's qualitatively similar to, there are these riddles about the perfectly rational pirates where like being able to commit to randomizing has similar interesting effects.
Yeah.
Okay. Any other questions for Florian?
Yes, I have a question, Florian. Thank you for this very interesting talk. I wanted to ask, have you considered other probability metrics rather than the Wasserstein metric in order to compute, for instance, integral probability metric or maximum mean discrepancy, and you found some problems with using those metrics?
So the proof actually we have is more general than what I showed you in terms of existence for Nash equilibrium, just to show that this ambiguity set needs to have a certain type of continuity property called hemi-continuity, which the Wasserstein distance has, but others may not have. That being said, we have not tried out other notions of ambiguity sets simply for the reason, so I said moments and KL divergence somewhat are inferior, but we have not tried others. We're quite happy with ours. Yeah. But to be understood also.
Yeah. Thank you. Thank you so much.
Okay, so I think with that we'll conclude. So thanks everybody for attending another Snap talk. The next edition of Snap will happen in a couple of weeks, so stay tuned for the announcement email there. All right, thanks again, Florian, and see you all soon.
Thank you. Bye-bye.